So, thank you. So where were we? This morning we introduced the idea of the chain rule equations. So everyone's familiar with the one variable chain rule, single variable calculus. The chain rule equations is the generalization of that idea to two dimensions. And we discussed this morning. So for a two-variable setting, so where you're looking at the domain of R2, and you're talking about functions defined in R2, you have one system of coordinates xy for R2, so that could be just the usual Cartesian system. Then in general, there might be another system of coordinates s and t. And what the chain rule of equations are is that equations that tell you what partial derivatives with respect to the new system of coordinates, s and t, so that's what's on the left, dz ds, dz dt, or you could read these as df ds, df dt, since z is equal to the value of f. It tells you what those partial derivatives in terms of the new coordinates are in terms of information relating to the old, the partial derivatives with respect to the old coordinates, so df dx, df dy we see here, and the partial derivatives of the transformation function between the two systems of coordinates. Okay. So this is the form they take for in the two-variable setting. They have the obvious generalization to more than two variables. So it's a so in the system where you're based in Rn, you've got n coordinates. Then you've got n different chain rule equations. Each one has this form here. So it's indexed by I. It's indexed by one of the new coordinates, si. So it's the same derivatives with respect to si that are being taken on the left and the right. The left-hand side you have df, dz, dsi. The right-hand side you have this linear combination of each of the partial derivatives of each of the old coordinates with respect to this new coordinate. And the coefficients in that partial derivative are, the coefficients in that linear combination are the partial derivatives of the original function f with respect to the original system of coordinates. Okay. Then we just ended last time this morning by just noticing that these chain rule equations could be put in quite a nice matrix form. So that same system of x, y, and st equations we were looking at a moment ago can be recast in terms of matrices like this. So you got the row vector of df ds, df dt equal to the row vector of df dx, df dy multiplied into this 2x2 matrix of partial derivatives. And so this is an important, significant matrix for us. We'll be using it later on when we're doing integration. And it's called the Jacobian, or the Jacobian matrix to be that matrix, or the Jacobian determinant to be its determinant. Okay, that'll be quite significant for us later on. So you've obviously got the exercises over the page to be working on for your next tutorials, and there's also an extra set of practice problems that I handed out this morning. Okay, so we might look at a few of these today. I thought I'd begin by looking at, it's actually one of the tutorial questions in the booklet, but looking at the Jacobian, we'll consider the Jacobian matrix and determinant of the transformation from our usual Cartesian coordinates to our polar coordinates. Okay. So remember, the polar coordinates is the way we locate a point in the plane by specifying its polar angle, theta, and its radial distance from the origin. And we can easily locate x and y in that picture too, the x coordinate and the y coordinate. And then the relationship between them can be read off from the right-angled triangle there, with theta is the angle, and r is the hypotenuse, and the relationship is x is r cosine theta, y is r sine theta. Okay. So that's the setup. Now the Jacobian, and it's written like this, dxy dr theta, this refers to the determinant of the matrix of partial derivatives. Now you need some way of just remembering how the notation goes. So it's dxy over dr theta. You can kind of think of it as xy, the old set of coordinates, r and theta are new. But the ones in the numerator are indexing the rows, and the ones in the denominator are indexing the columns. So the x is indexing the first row, so we have two partial derivatives of x in the first row, and we have two partial derivatives of y in the second row, and r is indexing, remember the ones in the denominator index the columns, so we got an r column and then a theta column. Okay. So these are all of the four possible first order partial derivatives of this transformation from the new coordinates back to the old coordinates. Now, the reason we're focusing on the determinant, it'll get a nice interpretation and function for us later on when we're looking at integrals. We're looking at integrating functions of many variables over regions in their domain. The Jacobian determinant will be an important part of the way we translate integrals from one coordinate system into another. Okay. That can be used as an evaluation technique sometimes for evaluating certain integrals. Again, different coordinate systems make sense in different contexts. So depending on what shape the region has that we're integrating over, that will dictate what the best coordinate system for that integral is. So these Jacobians have an important role to play in the way we translate integrals from one system into another. Okay. So what does this actually look like? Well, we have everything we need to evaluate this. The partial derivatives dx dr and dx d theta, well, dx dr will be cosine theta, dx d theta will be minus r sine theta. Then dy dr will be sine theta, and dy d theta will be r cosine theta. Okay, that's what the Jacobian determinant looks like. And this is a 2 by 2 determinant, so we can expand that without too much difficulty. Or well, to continue the theme of something you've been doing with Stephen is maybe we should try factorizing that using properties of determinants. And there's a common factor in that second row there, so I can take out the r, and I've left with cosine theta, sine theta, minus sine theta. And then we could go for straight expansion of the determinant, and we get cosine squared of theta plus sine squared of theta. Excuse me, which is of course equal to 1, isn't it? So the Jacobian just comes out as r. So we get this nice quantity r out. And, well, we'll understand the significance and the meaning of this later on when we're looking at integrals. This is kind of going to tell us what the relationship is between areas spanned by variations in the x and y coordinates and areas spanned by variations in the r and theta coordinates, and how that relationship changes depending on how far away you are from the origin. Okay. Just to give you a hint of what I'm talking about there, wherever you are in the plane, even if you're very, very far away from the origin, if you wobble the x coordinate a bit and wobble the y coordinate a bit, just introduce small changes in the x and y coordinate, the point will just vary over a small square in the plane. And that doesn't matter where in the plane you are. However, if you're at a certain point in the plane and you vary the radial distance a little bit, and you vary this polar angle theta a little bit, the size of the area that you're describing by those variations, it makes a difference where you are to begin with. if you're close to the origin, like this point here, and you vary the radius a bit and vary the angle a bit, what you describe is some kind of start off here, you vary the radius a bit, you kind of move in and out, you vary the polar angle a bit, maybe you move along these circular arcs, and you get this kind of rectangle-ish looking region with circular ends and straight ends along the radius there. Okay. So starting from some base point, varying the radius slightly, varying the polar angle theta slightly. However, if you are a long way from the origin, so this origin here is in relation to this point out here, if you vary the radius and the polar angle by the same amount, well, varying the radius by the same amount just still varies the radius by the same amount. But if you vary the polar angle now, you see the angles spread out as you move away from where they're centered at. So by varying the angle by the same amount here, okay, that's roughly the same angle. By the time it makes it out here to where the point is located, we're talking about a huge area. Okay. So varying the coordinates slightly describes the area of a region, and it has a dependence on where in the plane the point starts with. That's true for polar coordinates. It isn't true for Cartesian coordinates. For Cartesian coordinates, if I wobble the x and y coordinates, I just describe a small little square here, just as I would if I started close to the origin here. So this dependence on the initial radius is captured by this quantity here, by this value of this Jacobian determinant. Okay, and that will occur for us later on when we're looking at changing integrals. Now, before we tackle any of these problems here, any questions about that first of all? And we'll see this again when we're looking at our integrals over areas in the plane. So it's just a little bit of a look ahead to it. You'll see questions 5 and 6 there. They refer to what look like kind of closely related ideas, except they're based in 3 dimensions. So they're asking you to obtain Jacobian determinants related to what is known as spherical coordinates and cylindrical coordinates. Now, you may have seen these before, but you also may not have seen them, or may not have seen them in detail. So I'd just like to tell you about those now. So these are systems kind of like the polar coordinate system, but set in 3 dimensions. And again, they can, depending on what the context is, they can be much more useful or much more appropriate for describing regions in space rather than the x, y, and z coordinate Cartesian axes that we might be used to. These are 3D coordinate systems. 3D coordinate systems for questions 5 and 6. So the first one is spherical coordinates. Okay, so we'll describe these, and we'll describe them in relation to the usual. So here's what looks like the usual x, y, and z Cartesian coordinates in 3 dimensions. I think this is a right-handed system. Yeah, this is a right-handed system. So your thumb is x, your first finger is y, middle finger is z. Coordinate systems in 3 dimensions can come in a left-handed or a right-handed version, depending on whether this z is pointing up or pointing down, in relation to the way we've laid out x and y there. So you can think of y as kind of disappearing into the screen, x is kind of coming parallel to the screen, and z going straight up. Or think of these x, y, and z axes as just being the 3 edges emanating out of a corner on the floor. So you've got the 2 edges along the floor and the 1 vertical edge up along the wall. Okay. That's our 3-dimensional Cartesian coordinate system. It's a perfectly good coordinate system for 3 dimensions, but if things are happening in relation to circles or spheres, then it's not a particularly good coordinate system. So if we've got a point P out here, so imagine this kind of hovering out in space, hovering up here in the middle of the room somewhere in relation to the origin at the bottom left corner there. Another way of talking about the location of the point P is, well, we use the radial distance, the distance of the point P away from the origin. So the radial distance of the point P. We also we project the point P down onto the xy plane, this point P prime. So this is a right angle here. So it's the perpendicular projection of P down onto the xy plane. So wherever the point P is hovering up here, you just drop it straight down, vertically down onto the xy plane. That gives us this point P prime here. And we also get the projection of the radius here. Okay. And then there's these 2 angles. There's an angle theta here and an angle phi. So theta is the angle that the projected radius makes with the x-axis, and phi is the angle that the radius makes with the z-axis. So r is the radial distance from the origin to P. Theta, which is called the azimuth angle, is the angle between x-axis and the projected radius. And phi, which is called the zenith angle, the angle between the radius and the z-axis. Okay, so they've got these names, the azimuth angle and the zenith angle. And those 3 quantities, the radial distance and these 2 angles, they uniquely pin down the point P. Okay? So typically the radius is between, well, 0 and infinity. We're talking about points away from the origin. The azimuth angle might be between 0 and 2 pi. So the angle theta can go around the full circle. But then we only have to, then z should only go through a half circle then. Sorry, phi should only go through a half circle in order to capture all the points in 3D. So whenever things have a spherical aspect to them or are naturally described by these kind of quantities, then it would make sense to use this coordinate system. In this kind of coordinate system, for instance, will be used in astronomy. If you want to talk about, where your telescope is pointing, where the location of an object in the heavens is in relation to you, it makes a lot more sense to give its r, theta, and phi coordinates as opposed to its Cartesian coordinates. Well, for instance, we mightn't exactly know what the exact radial distance is of a particular star unless we do some, sophisticated measurements to actually determine how far away it is. But we can at least determine its location in the heavens where we're looking. It's a lot easier to give the angles theta and phi. Okay, theta. So if I'm here with my telescope, theta is the angle which describes, which way I'm pointing like this. Because as you vary theta, you would spin the point around the z-axis. So theta is me changing like this. And then the angle phi is how steeply I'm looking. Okay? So the angles theta and phi will uniquely pick out a direction into the universe from the origin, from myself. Okay. Then if we knew the radius r, that would uniquely pick out the location of the object. Okay. Now, how are they related to x, y, and z? What we would like is to know so we have the equations x is r cos theta, y is r sine theta in the two-dimensional polar coordinates case. What are the equivalent things here? Well, the easiest one you see there's a couple of rectangles here. There's another kind of equivalent rectangle hitting the z-axis there. So if you look at this rectangle up here, for which r is the hypotenuse, this quantity here along the z-axis, that will be the actual z-coordinate of the point P. And so the z-coordinate will be r times the cosine of phi. Okay. Then the length of this projected radius is the same as this length up here by equivalence. So this is involving a rectangle, a triangle with r as the hypotenuse and phi as the angle. So that's r sine phi. R sine phi is the length of this projected radius down there. And then that is the hypotenuse for this right angled triangle, which is r sine phi is the length of the hypotenuse, and the length of this side is x, the x-coordinate of the point P, and the length of this side, if you translate that over to there, you see that's y, the y-coordinate of the point P. So that's the quantity little x there, and bringing that up to there, that's the value of the coordinate little y, the y-coordinate of the point P. So then we're using this quantity r sine phi as the hypotenuse of this triangle. So then we just use the same idea as we had from the 2D polar coordinates. So it's cosine phi for the x, cosine theta for the x, sorry, and sine theta for the y. Okay. So those are the equations that tell you how the spherical polar coordinates are related to the Cartesian coordinates. Now, there's a warning attached to this that you just have to be aware of. It's one of the few, well, it's one of the cases in maths where the notation, there is no good commonly agreed notation. So different subjects and different books and different authors will interchange the letters theta and phi. Okay? Theta and phi. Phi and theta are used in different ways. Different ways in different subjects. Most mathematicians use theta and phi. So theta for this angle, phi for this angle up here. But engineers, physicists, astronomers, and so on, in the different subject disciplines, there exist different traditions for using them. So if you are reading a new source which talks about three-dimensional spherical coordinates, you need to just check what convention that author is following. They should make it clear. So that's the one mentioned in question 5. In question 6, we've got cylindrical coordinates. So cylindrical coordinates are so named because the kind of basic shape underlying the thing is a cylinder. The basic shape underlying this kind of system is a sphere. you think about keeping r fixed and varying theta and phi, that point P will move around the sphere of radius r, around the origin. Cylindrical coordinates, similarly, are based on the structure of a cylinder. So again, we've got a point P hovering up here. Now, the spherical coordinates were r, theta, phi. The cylindrical coordinates are rho, theta, z. So z is just the usual Cartesian z coordinate. So that features in the cylindrical coordinates as well. So we use the height of the point P above the xy plane. That is one of the cylindrical coordinates. Okay, so z, which is the vertical distance of P above the xy plane, or if z is negative, it's below the xy plane. That's one of the cylindrical coordinates. The quantity z. And the other two are related to the projected radius. So theta is, again, this same angle down here, and rho, some books will use r for this, but I'm using rho not to confuse it with it. So I'll reserve r just for talking about the actual radial distance. Rho is the length of the projected radius. Real radius is there, as always, from the origin to the point P. And the projected radius is that length, this length here, in the xy plane. Okay. So rho is the length of the projected radius, projected down onto the xy plane. Theta is the azimuth angle as before. And z is the z Cartesian coordinate. On this kind of coordinate system, if you think about what happens to the point P as you hold z fixed and you vary theta, well, P goes round in a circle around the z axis. You vary z, P just moves up and down this line. And as you vary rho, it will move out to a kind of a larger cylinder around the z axis. So the cylindrical coordinate system is very often used in 3 dimensions where there is some kind of circular symmetry around a central core. If there's some privileged direction in your setup, and it's a natural way to describe things in terms of circles around this central core. Maybe you've got a straight wire or something. Maybe you're talking about the magnetic force or something coming from a current flowing through the wire. That will depend crucially on what the radial distance of the point in space is from the center of the wire. So if you've got some idea of circles around a central core in 3 dimensions, then the cylindrical coordinate system is a very natural one. And again, we'd also want to know the relationship between the usual Cartesian coordinates and this new cylindrical coordinate system. Well, z is equal to z. It's the same z coordinate that's used in both systems. So it's a pretty trivial equation there. Then the other two equations just come from, again, considering this right-angled triangle down here. X will be rho cosine theta, and y will be rho sine theta. That's the Greek letter rho, lowercase rho. Okay. Okay, so with that now, you can now go and calculate, well, you can now go and answer questions 5 and 6. You'll be able to obtain the Jacobian determinants of these two systems. Now you have to proceed carefully because you'll be taking the determinant of a 3×3 matrix of partial derivatives. The 9 entries in the 3×3 matrix will have various of these coordinates in them. But the presence of the sines and the cosines, again, will lead to simplifications as you're expanding the determinant using that basic trigonometric identity that the sum of the squares of sine and cosine is 1. Sine squared plus cosine squared is 1. And these systems, we'll be making use of these when we're looking at integrals of functions defined in 3-dimensional space and performing integrals of them over certain 3-dimensional regions of the of space. Okay. Any questions just about the definitions of them and the terminology being used? Okay. Okay. So let's look at these. Let's look at some of these questions. Then, is everybody finished with that sheet? Yeah. Okay. So I'll scan these sheets as normal and put them up. So in the first question, we're given, again, this is quite similar to the question we did in the lectures. I might go through this now. So here we've got a differential expression in terms of the Cartesian coordinates, and we'd be interested in translating it into the new polar coordinate system. Okay. Questions 2 and 3 are kind of reminiscent of the questions we tackled using the small increments formula. So talking about these geometric quantities of volume and surface area, depending on a couple of variables, and what rate of change they experience when the parameters undergo changes. Question 4 relates to a point defined by a pair of parametric expressions. So we got a parametric description of the location of a point. So we got an independent variable t, which you could think of as time. And the x-coordinate and y-coordinate of this point are depending on time. And we'd be interested in, well, here we're asking what's the rate of change of the distance of the particle from the origin. How is that changing at a given moment in time, at time t equals 1. And then questions 5 and 6, asking you to obtain the Jacobian determinants of the transformations from Cartesian coordinates to spherical polar coordinates and cylindrical polar coordinates. Okay, so let's have a go at question 1 there. So this will be a similar approach. Similar approach to the example from the lectures. We're talking about Cartesian coordinates and polar coordinates. So the relationship between them is x equal to r cosine theta, y equals r sine theta. Or equivalently, the relationship going in the opposite direction is that the radius is, of course, the square root of the sum of the squares. And the angle theta is the inverse tan, arctangent, of the ratio y over x. It's actually this second form of them that we require for doing the translation of this. So to do the translation of this, I need to consider how to describe the partial derivative df dx in terms of the new coordinate system. So the chain rule equation tells me that this is going to be df dr by dr dx plus df d theta by dr d theta. Now we're dealing with an unknown, or with the general function f, so there's nothing I can do with df dr and df d theta. I don't have any description of f to develop those with. The only thing I can do some work on are these expressions here, dr dx and dr d theta. Now, just as in the lecture, dr dx, you see, I'll do this calculation down the side. Dr dx using the chain rule will be a half of x squared plus y squared to the minus a half multiplied by 2x. It's using the chain rule to differentiate r with respect to x. The 2's cancel, so we got x over the square root of the sum of the squares, or for the moment, a compact way of writing that is x over r. By symmetry, we'll need it later, dr dy will be y over r, because x and y play exactly the same role in the function for r, so the derivative with respect to y will be the very same similar expression. Sorry, I wrote down the wrong thing there. That's d theta dx there. Sorry, d theta dx. And then as we looked at in the lecture, differentiating theta with respect to x, well, again, I need to use the chain rule. The derivative of inverse tan is 1 over the square of the argument plus 1. So this will be 1 over y over x all squared plus 1. That's the derivative of the inverse tan part. Then you multiply by the derivative of the inner part. Well, the derivative of y over x with respect to x is minus y over x squared. Okay, differentiating x to the power minus 1. So that looks like a big mess there, except it would benefit from multiplying above and below by x squared, because there's an x squared in the denominator, both above the line and below the line. When you do that, you get minus y over x squared plus y squared, but that can be written even more compactly as minus y over r squared. And then for translating df dy, I'll also need d theta dy. And d theta dy can be calculated in a similar way. So first, differentiating the inverse tan, I get 1 over the square of y over x plus 1. Then multiplied by the derivative with respect to y of the inner argument, y over x. So that's just, what is it, 1 over x. And again, we can kind of tidy up the denominator by turning it into r squared, by multiplying the denominator by x squared. So let's do the same to the numerator, and we'll recover x over r squared. So multiplying above and below by x squared, so we got y squared plus x squared in the bottom, that's r squared. And you get x squared over x, which is just x on the top. So that's really where all the work is. So now we can bring these things into the chain rule equations. So dr dx is x over r. So I'll have x over r df dr plus d theta dx minus y over r squared df d theta. So that's the expression for df dx. Then df dy, by the chain rule equation, this is df dr, dr dy, plus df d theta dy. So the dr dy and the d theta dy I take from the right-hand side there. I've just worked those out. So dr dy is y over r df dr, and d theta dy is x over r squared df d theta. So I now have kind of a more or less, well, not quite, but I've done as much as I can to translate df dx and df dy into expressions just involving r and theta. Okay, I still have a few x's and y's around, but we'll see what the joint effect of those is shortly. So as asked for, I was asked to look at the sum of the squares of these two expressions. You take df dx all squared plus df dy all squared. That's a question of how much of this stuff you do in your head, how much you kind of write it all out. Let's look at what we got. Well, we're going to have some squares of the derivative df dr. Okay? So we'll get squares of the derivative df dr. And what coefficient does that have? Well, I've got x squared over r squared plus y squared over r squared. So if x squared plus y squared over r squared, and what's another name for that? X squared plus y squared over r squared? That's a much simpler name. What would you rather say than x squared plus y squared over r squared? Someone whisper it? 1. So that's nice. So we just get the square root of df dr. We also have some squares of df d theta. And what's the coefficient there? I'm going to get x squared over r to the 4. X squared over r to the 4 from there, and from here I get y squared over r to the 4. So I get x squared plus y squared over r to the 4, or that has a nicer name. One over r squared, yeah. Got r squared on the top and r to the 4 on the bottom, so you got 1 over r squared. Then we've got the cross terms, which are the products df dr times df d theta. So what do we have? How many of those do we have? So if we square this expression, we get minus 2 times xy over r cubed plus 2 times xy over r cubed. So that's going to cancel. Minus 2xy over r cubed plus 2xy over r cubed. So that has a much nicer name, namely 0. Okay, so just carefully squaring both of these expressions and adding them together. So this simplifies quite a lot. It's df dr, all of it squared, plus 1 over r squared times the square of df d theta squared. So this is the equivalent expression expressed in polar coordinates for that original expression df dx all squared plus df dy all squared. Okay? So we're seeing how to use the chain rule equations to take differential expressions expressed in terms of one coordinate system and take them into another coordinate system. Okay, and one of the main core problems of mathematics is obtaining solutions to differential equations, because those are what come up when you look at any kind of mathematical modeling of the real world. And so we need to be able to know how to manipulate these equations and translate them, so to speak, into different coordinate systems. Okay? Depending on what the context is, some coordinate systems are better suited to describing the thing rather than other coordinate systems. Okay, anything I could clarify on that expression there? Okay. So it does all start with being, able to get these chain rule equations down correctly, and then taking them from there. Okay, so you got a whole bunch of things to be working on. The tutorial exercises from the booklet, the rest of those exercises on the extra problem sheet. my aim is just to give you plenty, you know, I don't want anybody to be at a loose end, so there's plenty of work to be getting on with there. So next week we'll have a lecture, and I think next Monday evening, when Stephen sees you, he'll be handing out the coursework sheets, and not off with that. Okay? Okay, so thanks a lot. I'll be scanning these and putting these up underneath the recording as usual.